want to say thank you to the organizers for the generous invitation to speak. Pleasure to be back here at the ICMS and in particular to be celebrating the life and work of Professor Lenstra. Right, so let me get started by talking about the application that motivates this work. I should say this is joint work with Affine Siad and Arul Shankar, who's here. The motivation today is to study the distribution of the two class groups, which I mean the two torsion subgroups of the class groups, and families of cubic member fields. Okay, so regarding this distribution, we have the following well-known theorem of Bhargava from his thesis. Bhargava proves that when totally real or complex cubic fields K are ordered by the absolute values of their discriminants, the average over K of the size of the two torsion subgroup, the class group of OK, is given by 5/4 in the totally real case and by 3/2 in the complex case. So this result, I think it's fair to say, is one of very few cases of the heuristics of Cohen-Lenstra and Cohen-Martinet that has ever been proven. I'll just mention a couple other cases that are known. The foundational work of Davenport and Heilbronn from 50 years ago established or determined the average size of the three torsion in the class groups of quadratic fields. And more recently, there's work of Oliver, Wang, and Wood. 2021, and they studied the average three torsion in certain relative class groups associated to two extensions established in other case heuristics. But we don't know very much more than that.
Cleaners do something too,
Right?
and cleaners, didn't they do something?
Yeah, so that's about Smith and Smith. So that's about sort of two power torsion in class groups of quadratic fields, which I guess technically would fall under the heuristics of Cohen, Martinet, Girth. I didn't mention Girth.
Bhargavas, I guess, right?
Sorry?
Bhargavas also fall into that.
Yeah, so previously I excluded the name Girth. So I didn't, so yeah, I guess the two power torsion.
Yeah, Cohen and Martinet conjecture about the two part of cubic is good for that representation of S3. So that's already in Cohen Martinet.
Yes, so a key ingredient in the proof, can people see what I write here? Okay. The key ingredient in the proof of Bhargava's theorem is an explicit parameterization of cubic number fields in terms of binary cubic forms. And this is known as the Delaunay-Ladeev correspondence. And what this correspondence says is that if you have a binary cubic form, by which I mean a homogeneous polynomial of degree 3 in two variables over the integers, let's call it F. And you can write down a ring RF, which you could define a ring of global sections of the subscheme of P1 cut out by the binary cubic F. And this assignment that takes a binary cubic F to the corresponding ring RF defines a bijection between GL2Z orbits of binary cubics. So what do I mean by a GL2Z orbit of binary cubic? Well, the group GL2Z acts on binary cubics by a linear substitution of variable. So that's the action. We get a bijection between these GL2Z orbits of binary cubics and cubic rings taken up to isomorphs. This Delaunay-Faddeev correspondence gives an explicit parametrization of cubic number fields and more generally of cubic rings. That plays a key role in the proof of Archibald's theorem. Given that we have this way of parametrizing cubic fields, it's natural to ask, well, what happens to the average two torsion in the class group when we order cubic fields not by their discriminants, but by the heights of their defining binary cubic forms? And this question was studied in work of Bunker and Varma. In 2018. And they proved that when binary cubics F the integers such that Rf is equal to the ring of integers of a totally real or complex cubic field are ordered by the sizes of their coefficients and the average over such F of the size of the two torsion in the class group RF is given by 5/4 in the real case and 3/2 in the complex case. This result shows that even if you change the ordering of cubic fields from discriminant to the heights of the defining binary cubic forms, the average two torsion in the class group stays the same, indicating that these distributions are in some sense robust under this change of height. And so I'll make a further remark. People can't see that. Maybe that's a little too hard.
Here, reach that height. Oh, okay, anyway.
I'll make a remark, which is that in both of these theorems, the averages remain stable under the imposition of quite general infinite sets of local conditions. So for example, in Archibald's theorem, you could restrict to a subfamily of cubic fields satisfying ramification conditions. Or in the theorem of Bunker and Varma, you could just look at those binary cubic forms where the x² coefficient is divisible by 37. And the averages would stay the same. These are insensitive to local conditions, which raises the question, what about global conditions? So an example of a global condition would be to consider a family which I'll denote UAZ, which is going to be a subset of binary cubics F such that the x cubed coefficient of f, namely f of 1 comma 0, is equal to some fixed a. So as an example, you could take a to be 1, in which case it's easy to see that the ring RF is simply z adjoin x mod f of x comma 1. And in this case, we say that the ring RF is monogenic because it's given by adjoining to z a root of f. So in this case, we have the following theorem. So before I state the theorem, let me introduce some notation. So this is notation for the theorem. So given f in UAZ, we say that it is right sufficiently ramified. I will henceforth abbreviate RSR. If for all primes p, such that the p-adic valuation of this fixed a is odd, so p divides a with odd multiplicity, if we look at the subscheme defined by f, sitting inside p1 over fp, we want this to have a double point away from infinity, p1 of fp, or a triple point at infinity. So being right sufficiently ramified amounts to some kind of ramification conditions of the cubic field. Notation, and then given that, we have the following theorem, which is due to Bhargava, Henke, and Shankar from 2019. They proved that in binary cubics f in UAZ, so this family of binary cubics with fixed x cubed coefficient a, such that RF is the ring of integers of a totally real complex field. Ordered by the sizes of their roots. So the height function here is a little bit different, but averages are pretty insensitive to height, so it doesn't really matter. So when these binary cubics with fixed x cubed coefficient equal to a are ordered by the sizes of their roots, it turns out that the average over f, such that f is right sufficiently ramified of the size of the two torsion in the class group, is given by 3/2 in the totally real case and by 2 in the complex case. Notice that that is an increase relative to theorems of Shankar, Verma, and Bhargava for the full family of cubic fields. So this is the situation when f is right sufficiently ramified, and they also show that when you average over those f's that are not right sufficiently ramified, you get 5/4 and 3/2 as before. So the upshot is when you fix this x cubed coefficient a, your family of cubics partitions naturally into two subfamilies, one on which you get the expected averages, and one on which the average seems to increase quite mysteriously.
Doesn't that make it wrong sufficiently ramified?
Well, I will in just a moment introduce the notion of left sufficiently ramified.
What's the density of the right sufficiently ramified cubic ones?
Yeah, so I think the density of the right sufficiently ramified is the product over primes P dividing A. Oh, yeah, P, A, odd 1 over P plus 1. I think that's what it is.
Seems reasonable, thanks.
As you can see, that density goes to 0 pretty quickly as A picks up prime factors, which is why you don't see this extra contribution for the full family of cubics. Okay. So that's what happens when you fix one coefficient of your binary cubics. Next question is, what happens when we fix two coefficients? An even thinner family of binary cubics. So in this regard, consider UAD Z, which is going to be the subset of binary cubics F such that F of 1 comma 0, the x cubed coefficient is A, and F of 0 comma 1, the y cubed coefficient is D. As an example, you could take A and D to both be 1. And in this case, bring RF is of the form Z adjoin theta, where theta is a unit. So the ring RF, you could say, is monogenized by a unit. You could ask, well, for a family like this, what is the average two torsion in the class group? And so in this regard, we have, oh, I should set the notation. Here's where I will define the notion of left sufficient ramification. So given F in UADZ, we say that it is left sufficiently ramified, which I will abbreviate as LSR. If for all primes P such that divides D to odd degree, again, the same sort of condition. You look at this subscheme over FP, this should have a double point away from 0. Or a triple point at 0. So that's the notion of left sufficient ramification, perfectly opposite to the notion of right sufficient ramification. Then state the theorem. We just posted our preprint a week ago, so you can find that on the archive. So consider binary cubics F in this family UADZ, where A and D are fixed non-zero integers. Such that RF is the ring of integers. Of a totally real or complex cubic field. Then when such cubics are ordered by the sizes of their roots, so again, the same height function from Bhargava-Hankey-Shankar. We get the following averages. So the average over F that are both left sufficiently ramified and right sufficiently ramified. Oh, I should make an assumption here. So let's assume. This is just for simplicity. It's not necessary to assume this. Let's just assume that A and D are coprime and A and D are odd. These are just assumptions so that I can state the theorem in a simple way, but we don't actually need to assume these things. Under those assumptions, the average over F that are both left sufficiently ramified and right sufficiently ramified of the two torsion in the class group is given by 2 in the totally real case, and rather strangely by 3 plus 3 over 14 in the complex case. So what we actually prove is the average is bounded by 2 and bounded by 3 plus 3 over 14. I'm going to put a star in the inequality to indicate that conditional on a tail estimate, we can prove equality. To really think of 2 and 3 plus 3 over 14 as being the exact averages.
Excuse me, since it should be symmetrical in A and D, shouldn't the size of the inverse roots play a role also?
Size of the roots. Well, actually, I think these averages are stable under flipping A and D. So this is what happens when we're both left sufficiently ramified and right sufficiently ramified. Alternatively, you could look at just those F's that are left sufficiently ramified and not right sufficiently ramified, or not left sufficiently ramified and right sufficiently ramified of the same portion in the class group. And we prove that this average is bounded with conditional equality by 3 halves in the real case and by 2 in the complex case. So the 3 halves and 2 should be familiar. That's what you get when you just fix one coefficient.
Wait, Ashwin,
Yep.
what exactly are sizes of the roots? Is it the Bay height of the roots in P1?
Size of the roots. I mean, the roots are some real numbers and absolute values of them.
Well, they're pairs, right? X and Y.
Okay. Well, I mean, if you think of the polynomial f of x comma 1, some polynomial, it has some roots and real numbers, and the size of the roots, I mean.
1, okay.
So when you're left sufficiently ramified and not right sufficiently ramified, or the reverse of that, you get 3 halves and 2, which are averages that we saw before. And the last case is the average over F that are both not left sufficiently ramified and not right sufficiently ramified. In that case, the averages turn out to be 5/4 and 3 halves. That's our main theorem. And yeah, so I want to remark about this 3 over 14. 3 over 14 is very strange. And the reason is the following. So over cubic fields. K. We have the following sort of general expectation. We sort of expect that the average over K, the size of OK cross mod OK cross squared times the number of surjections of the two torsion in the class group onto Z mod 2. Sorry, yeah. We expect that this should be independent of the real signature. That is to say, if you went over real cubic fields or complex cubic fields, this average size should be independent of signature. And that's actually easy to verify. Do I still have this theorem up here? Probably not. I mean, it's easy to verify, for example, in this Vargava-Henke-Shankar result, that average I wrote down there would be 2 for both the real and complex cases. Here that average would be 1 in both the real and complex cases. You just do that. And similarly for this theorem, in these cases, again, you get an average of 2, average of 1. But here, if you compute this average in the totally real case, you get 4. In the complex case, you get 4 plus 3 over 7. There's some kind of breaking of symmetry between the totally real and complex cases that happens when your binary cubics are both left and right sufficiently ramified. Not sure why that happens, but that's what we see. The rest of the talk, I want to sort of briefly describe the proof. And the way these theorems are proven is by means of a 2-step process. And the first step of the process is to parameterize the arithmetic object of interest. So what we do is we realize arithmetic objects of interest. In this case, 2 torsion classes of cubic fields in terms of the integral orbits representation of a group G acting on a vector space W. So for this particular application, 2 torsion and class groups of cubic fields, W is going to be the space of pairs A and B of ternary quadratic forms. By ternary quadratic form, I mean a homogeneous polynomial in 3 variables of degree 2. And the group G is going to be the group SL3. Now, what is the action? Well, SL3 acts on W via linear substitution of variable. One way to think of this action is G acting on a pair A comma B. Well, you can think of both A and B as being symmetric 3x3 matrices. And then the action is just GAG transpose, GB transpose. And a nice fact about this action is that the ring of polynomial invariant functions is generated freely over the integers by the coefficients of the following polynomial: 4 times the determinant XA minus YB. As I mentioned, you can think of A and B, these ternary quadratic forms, as being 3x3 symmetric matrices. So then it makes sense to think about the determinant of XA minus YB. And this is in fact a binary cubic form that with coefficients, polynomials in the entries of A and B. The core is to make it integral. So these are A and B are integral ternary quadratic forms, and when you write them as a matrix, you get halves on the. Okay. So that's the representation. And then the parametrization result is as follows. This is the parametrization used by Bhargava in his thesis. So let F be a binary cubic form over the integers. Such that RF is equal to the ring of integers then we have a natural injection from the non-trivial elements of the dual of the two torsion in the class group into the space of pairs of ternary quadratic forms A and B with integer coefficients such that the following condition is satisfied. So what do I mean by this? Well, A and B are ternary quadratic forms. They cut out plane conics, and so it makes sense to talk about the Q points of A and the Q points of B. And the condition is that A and B have no Q points in common. That's one condition. And then the next condition is that this funny polynomial 4 times the determinant of XA minus YB has to equal our original binary. We're interested in the space of these pairs AB taken up to the action of the group. So it's easy. I stated this as an injection. The image is defined by conditions over the reals, and Bhargava in fact says exactly what the conditions are. So this is in fact a parameterization of the two torsions of class groups of cubic fields. That's what we'll be using. Okay. Some notation. Non-zero integers A and D. Let WAD be the variety of pairs AB such that the determinant of A is A and the determinant of B is D. Well, I should actually I should say A over 4 and D over 4. Yeah. Okay, so why am I looking at this? Well, as in this parameterization, we've got pairs AB, WZ, such that 4 times the determinant of XA minus YB equals f of x comma y. So if we're going to fix f of 1 comma 0 to be A and f of 0 comma 1 to be D, then what we want is the determinant of A to be little a over 4 and the determinant of B to be little d over 4. But that's why we're interested in this subvariety, WAD. And then proving our theorem on the average two torsion in the class group effectively amounts to determining an asymptotic count of the number of SL3Z orbits on this variety, WADZ. And we'll also have to be able to do this count imposing local conditions on the orbits that we want to count. Trying to count these integral orbits lying on this variety. And now let me explain how we go about doing that. So this is the second step of the proof strategy, counting. We view the integral orbits as lattice points in a fundamental set F for the action of SL3Z and the real points of W. But of course, we're not interested in counting all of those lattice points. We're only interested in counting those lattice points that lie on the subvariety WADR. Okay. Now I'm going to make an explicit choice of F. Take F to be F1 times F2, where F1 is a fundamental domain for the action of SL3Z on SL3R. And F2 is going to be a fundamental domain, the action of SL3R on W of R. So if you choose F1 and F2 like that and multiply them together, you get essentially a fundamental domain for the action of SL3Z on W of R. But in fact, will not work with just this one fundamental domain F. It turns out to be more effective to work with a continuous family of fundamental domains. So this is an averaging technique due to Bhargava. So it's more effective to average over a continuous family fundamental sets. And in order to achieve this, we'll just take a subset G naught in SL3 var. G naught is going to be closure of a non-empty open bounded subset. Of volume 1. And then what we'll do is we'll count the lattice points not in F, but in F1, G naught, F2. We're kind of sort of varying this fundamental domain using the set G naught. Count the points in this sort of total space, and then we'll just divide out by the volume of G naught. That'll give us the desired count. Before I continue, I'm going to just set some notation. For a set S and W of R, let S sub X be the set of pairs A, B, and S, such that the roots of 4 times the determinant XA minus YB are at most X in size. And for a set S in WZ, let S superscript ir is short for irreducible, be the set of pairs AB in S, such that this condition that the Q points of A and the Q points of B are disjoint. That's fine. Then what we want is the following count. We want the number of points WADZ here that lie in our fundamental set and that have height up to X. That's really the count that we want an asymptotic for. And this is just tautologically equal to the following. This is just tautologically equal to the integral over G and G naught of the number of points WADZ here intersected with this fundamental domain with a little g sandwich in between. Points of height up to X. This is a tautology. And the reason is that the number of points in a fundamental domain should be independent of the choice of fundamental domain. And when we sandwich a little g in between F1 and F2, we get a perfectly good fundamental domain. That's the qualities of tautology, but instead of integrating over G and G naught, we can integrate over this F1. If we do that, little change of variables, we get number of points in WADC here intersected with G naught. And I can move the height up to X condition inside like that. And now we want to evaluate this integral. Okay, so I'll first make some simplifications. If we look at the fundamental domain F1, this consists of a main body, which I'll denote F1 main, and a cusp, I'll denote F1 cusp. So very crudely, you could think of the fundamental domain as looking like this. And then the sort of round region here is F1 main. And then this sort of cuspidal region going off to infinity is the cusp. Then we can show using elementary methods that the integral over the cusp, if we just take that integral over there and restrict it to the cuspidal region, so this is the number of points UADC here, intersected with G naught, F2 of height up to X, you can show that this is negligible. So I say that this can be proven using elementary methods, but in some sense, this is the hardest part of the proof. And it involves sort of counting by hand the number of symmetric matrices of a fixed determinant in a very skewed region. And to do that, we sort of exploit the particular structure of the determinant formula for a symmetric 3x3 matrix. That is done using elementary methods, and we can also show using local methods together with the sieve that we integrate over the main body the complement of WADZ here. So the complement of WADZ here would be space of pairs AB where A and B have a Q point in common. this integral, this is also negligible. Those are two facts that'll help us simplify the integral that we really want to compute. The integral that we really want, thus, number of points in WADZ here lying in the fundamental domain tied up to X is just the integral over the main body of number of points in WADZ with no ear superscript lying in this region, GG naught F2 of tied up to X dg. That simplified our integral a little bit. And now I should note that all of these steps so far kind of work for the proof of Vargaba's original theorem. And in that case, the integrand, so I guess in Vargaba's theorem, the very first theorem I mentioned, the full family of cubics, the integrand was the number of points in W of Z intersected with GG naught F2 right up to X. So he wasn't fixing A and D, and so he just got all of W of Z. And how would you sort of estimate this integrand? Well, W is an affine space, and GG naught F2X is a region in that affine space. So the number of points in that region is, by Davenport's lemma, roughly the volume of the region. So this turns out to be roughly the volume of GG naught F2X. Now we can't apply quite the same reasoning to estimate this integrand, because WAD is not an affine space, some funny variety. So in order to estimate the integrand, what we do is we realize WADZ as the set lattice points in a union of products of symmetric R varieties. There are methods, various methods for counting lattice points on symmetric R varieties, and we'll apply those methods.
Symmetric.
I'll explain that in just a second. A bit about symmetric varieties. At least in the context of ternary quadratic form. We'll let V be the space of ternary quadratic forms. And let VA be the space of forms where the determinant of A is little a by 4, then for A in VA of Z and a ring R, let SA of R be defined to be SL3 of R mod SOA of R. So here, this group SOA is the orthogonal group that preserves the ternary quadratic form A. I'm gonna just define SA of R to be this quotient. Then the map IA from SL3 of the reals, the VA of the reals, defined by G goes to GAG transpose, induces an injection SA of R into VA of R. So here, SA of R is the symmetric R variety associated with the ternary quadratic form A. That's what a symmetric R variety is in our context, but of course, you define it more generally. If you have a group G and a subgroup preserved by an involution, call that subgroup H, then you could define a symmetric R variety, namely G of R mod H of R. We get this injection. And moreover, if you look at the disjoint union over SL3Z equivalence classes of ternary quadratic forms A with this determinant little a by 4, that disjoint union of SA of Z, well, under these injections, that's just the disjoint union over equivalence classes of A's of pi A of SL3Z, but this is just all of VAZ. That is to say, the ternary quadratic forms with determinant A, you can really think of them as being this, think of them as being like points in these symmetric varieties SA of Z. And this disjoint union is finite. So counting points in VA of Z is like counting points in each of these finitely many SA of Z's. So the upshot is that counting lattice points in WADR, which is also the same as VA cross VD of R, amounts to counting points in SA cross SB of Z sitting inside SA cross SB of R for each choice of capital A and V little a of Z and capital B and V little d of Z. So our problem boils down to counting integral points on these products of symmetric R varieties. And the problem of counting integral points on symmetric R varieties was solved by, well, various people, but a particularly convenient form by Eskin and McMullen in 1993. They used dynamical methods to prove this theorem, and the version of the theorem I'm going to state follows from combining their work with work of Rodnick, O, and Shaw from 2009. So you combine those two works to get the following results. So let curly B in VA of R be non-empty open bounded subset with smooth boundary. And for x greater than 0, let curly b sub x be the scale of x, or the scale of b by x intersected with SA of R. So here, A is some fixed ternary quadratic form with determinant little a over 4. Then they prove that the number of integral points in SA well, what should I? Lying in this region Bx is asymptotic to the following. There's a constant out front, and the constant is fundamental volume of the group SOA divided by the fundamental volume of the group SL3 times the volume of the region Bx. So here the volumes are computed with respect to the natural Haar measures on all of these spaces. Basically, what Eskin-McMullen proved is that the number of points in a region of a symmetric variety is the volume of that region with some constants. And this result was, I should say, was made effective with a power-saving error term by Benoit and O in 2012. So our problem amounted to counting integral points on products of symmetric varieties, and that problem was solved by Eskin-McMullen and with power-saving error term by Benoit O, and so we can apply those results through our theorems. So in the last few minutes, briefly mention another result that we can prove using this method. So the two torsion in the class group of a monogenic cubic field is very closely related to two-Selmer group and the associated elliptic curves. And so we can prove theorems about two-Selmer groups of elliptic curves as well. Very briefly. Let D be an integer that's 1 mod 8. Then the average over cubics F in U1 DZ. So maybe I should, I don't know if I define this before. Yeah, so let U1 DZ be the space of binary cubics such that F of 1, 0 is equal to 1 and F of 0, 1 is equal to D. The average over those F's such that the discriminant of F is square free and such that F can impose some local conditions of 2. So F is congruent to x cubed plus xy squared plus y cubed mod 8. And such that F is left sufficiently ramified. The average over that family of the size of the two-Selmer group of the elliptic curve y squared equals f of x comma 1 is at most 6 with equality conditional on a tail lesson. And similarly, the average over the same family where F is not left sufficiently ramified of the size of same thing, just on a group of this elliptic curve that average is at most 3 with a quality conditional on tail estimate. So you might ask, well, why when F is left sufficiently ramified does the average double? And the reason is that when F is left sufficiently ramified, you can sort of write down a distinguished two-Selmer element, and we expect 100% of the time that that distinguished two-Selmer element contributes an extra generator to the two-Selmer group. The average size should be twice. Yeah, so that's my talk. Thanks so much.